What if you could build deep learning systems in a language that is not only fast, but also memory safe, energy efficient, and highly reliable? Most people associate AI development with Python, and that makes sense. Python dominates the machine learning world. But when performance, stability, and system level control start to matter, another language becomes extremely interesting: Rust. In this series, we'll explore deep learning from the ground up, and we'll do it through the Rust ecosystem. I know what you're thinking. Why would I use Rust for deep learning when I already have Python and PyTorch? And that's a fair question. The short answer? Python is 70 times slower than Rust in compute-intensive workloads. That's not an exaggeration, it's a real benchmark. In this series, we will build neural networks from scratch. In today's episode, we do the full environment setup and write the first program. Let's get started. Let's look at the concrete numbers. A benchmark across multiple programming languages. C has a time complexity factor of 1.00. That's the baseline, the fastest. Rust comes in at 1.04. C++ at 1.56. Java at 1.89. And Python 71.90. That means Python is nearly 72 times slower than C for compute-intensive numerical work. This is a real problem when you're training a model with millions of parameters. But it's not just speed. Rust has two more major advantages for AI. First, memory safety without a garbage collector. Rust knows at compile time that you have no memory leaks, dangling pointers, or race conditions. That means your programs will not crash in production due to weird memory issues. Second, correct concurrency. Rust makes it impossible to have data races between threads. When training a model and parallelizing operations across multiple cores, Rust protects you from bugs that in Python only appear occasionally and are nearly impossible to debug. Let's move directly to practice. You can perform these exercises on any operating system, but I will be using Windows. My computer has an AMD Ryzen 64GB of RAM and an NVIDIA RTX 4000 ADA generation GPU. For the beginning, we start with a simple script. In Rust, the ndarray crate provides powerful data structures for numerical computing. You can think of it as something similar to NumPy in Python. It allows us to work with vectors, matrices, and multidimensional arrays, which are essential for scientific computing, machine learning, and deep learning. In this small example, we import array from the ndarray crate and create a simple array from a Rust vector. Here, from_vec converts a standard Rust vec into an ndarray array structure. Once the data is stored in the Rust structure, we import a distrum stored in the Rust charge and Arthur example stored. In the script, we can easily perform video vector operations, matrix operations, slicing, broadcasting, and many other numerical computations. This is why ndarray is widely used in the Rust ecosystem for machine learning and deep learning libraries. If the output shows the array, it means the dependency was added successfully and everything is working correctly. The output should look like this. Now let's look at a slightly more interesting example. Instead of just creating an array, we create two vectors and add them together. The RNG library allows us to perform vector operations directly, which is very useful for numerical computing and machine learning. As you can see, the result is computed element-wise. Now let's look at a more interesting example: matrix multiplication. This operation is fundamental in machine learning and deep learning because neural networks are built mostly from matrix operations. Here we create two matrices and multiply them using the dot function provided by the Arandaki crate. As you can see, Rust allows us to perform these numerical computations in a very clean and efficient way. Before finishing, let's look at a small example inspired by neural networks. Here, we take an input vector, multiply it with a weight matrix, and apply a ReLU activation function. This is essentially what happens inside the neural network layer. As you can see, with ndarray, we can implement these operations in developers just a few lines of Rust. And with this small example, you've seen how we can use the ndarray crate in Rust to work with vectors, matrices, and even simple neural network-like computations. These kinds of numerical operations are the foundation of machine learning and deep learning systems. In the next videos, we'll go deeper and explore more advanced concepts and libraries for AI development in Rust.